Thanks very much for having us here, and it's great to be here today. So my name is Peiyao Shang. I'm currently a researcher at Shang, and I'm here with my co-author Zerui Cheng. He's a PhD student at Princeton University. So today we are going to talk about our work on this LiveCodeBench Pro. This is a benchmark evaluating how well today's AI model really perform in competitive programming. So this is a joint work with an incredible group of collaborators from many universities and also from Shang. So I want to acknowledge their contributions right at the start. So then starting from our motivation. So at Shang, we are driving the development of AI that is community built and community owned. And right now, though, we know that open source AI still lags behind a bit of the closed system in two aspects. One is capability and the monetization. So a few weeks ago, I believe my co-founder Himanshu was also here sharing how we are addressing the monetization challenge by leveraging our fingerprinting technology to check the model ownership and ensure the loyalty. And today I want to focus on the other side of this grand challenge, capability. And specifically, we will explore how well today's model perform on one of this most challenging and high impact problem, coding. So AI for coding, I believe, undoubtedly the killer app of generative AI, at least for me, or I'm sure for many of us whose daily work revolves around writing codes. So it covers a wide range of applications like competitive programming, also engineering side, software development, or other like specialized domains. And in our work, we focus on competitive programming because it's a perfect testbed for AI capabilities. First, it supports fully automated evaluation, so there's no human in the loop. And second, the correctness is purely objective. So your solution either passes all tests or it doesn't. And third, it's challenging enough to require genuine reasoning and problem-solving ability. So it's not just like pattern matching or memorization of all these problems. And we've also seen how AI has transformed the code development with all these powerful coding assistants. And AI models are even cracking the toughest programming competitions. Just earlier this week, I believe all of you have seen this news that OpenAI announced that their reasoning system won gold medal, like at the IOI online competition. And they're ranking number 6, even among the humans. So these kind of live contexts like IOI are the perfect proving ground for those coding ability, but it only takes place once a year and not every model gets the chance to compete there. So to evaluate a broader set of models, the most widely used benchmark is called LiveCodeBench, which collects a large set of competitive programming problems across different difficulty levels. And on its recent leaderboard, we can see in the picture that the numbers look remarkable as the top models are solving over 80% of all these problems, and the best pass rate of the hard tier of problems exceed 63%. So, and from another side, beyond these benchmarks, a more human comparable view is through this LO rating. For example, also like 8 months ago, OpenAI has reported estimated code forces rating of all of their models, and among which GPT-03 achieved a rating of 2,727. So this is roughly the top 0.2% of human contestants. This was quite impressive and raised a lot of discussion at the time. So do these results look very promising, truly mean that many AI models have already outperformed human experts in competitive programming? When we take a closer look at like how the scores are actually estimated and calculated, the answer is probably not. This is because the existing benchmarks often don't reflect the real-world challenges. In fact, there are several issues that can cause these estimates to be too positive and to be inflated. The first problem is data contamination. So even though benchmarks like LiveCodeBench, so they're live, they will update the problems every like 3 or 4 months, But in reality, those contest problems and their solutions often get posted publicly just days after a contest. So if a model has the web search tools, it could easily retrieve those solutions during testing. And the second problem is weak unit test. Some problems only include their public test cases, which don't cover all these tricky edge cases. So models, if they can pass this provided test without actually solving the problem correctly, then it will create a lot of false positives and also the inflated score. And the third point is the difficulty level. So looking at the LiveCodeBench leaderboard, there are many models. They have scores clustered very closely to each other. This means the difficulty distribution of these problems isn't well balanced. So, and it will also limit how well we can differentiate those strong models from weaker ones. And the last point is there's no human baseline or diagnostics. So because if we are not comparing with human directly, or we don't have a breakdown of what is the strengths, weaknesses of the model, then it's hard to interpret what is a good score. What is a good score really means. Is it a model consistently strong across different problem types, or it's just excelling in a very narrow subset? So to address all these shortcomings, we set out to design something more rigorous, something more realistic to test these genuine coding and algorithmic reasoning abilities of all of these SOTA models. And so we proposed this LiveCodeBench Pro, and each problem in this benchmark is created and annotated by some of the best competitive programmers in the world. So I will list them here. They are all the community behind this work, including our authors, but beyond. For example, Zerui is one of our lead authors, and he's also still actively participating in all these competitions recently. And many others, there are NOI medalists, ICPC World finalists. They're also experienced problem setters, contributing to those platforms like Codeforces for a long time. So that means they not only know how to solve problems, but also know how to actually design and evaluate them, evaluate the coding ability of others. And we also have many leading AI researchers from different universities, industries. So that's the expertise powering this community-built benchmark. And to introduce this benchmark, we have a website. This is live, and you can see the leaderboard and some detailed evaluation results. You can access it through the QR code here, or just type livecodebenchpro.com. So we can call it LiveCodeBench Pro because we have these advantages to solve the issues we've mentioned before. First, the problem set. We source a lot of problems directly from the live contests, and we'll update this set frequently. They are all collected before any public solutions are released, so there's no risk of training or inferencing data contamination. And we also utilize the online judge platforms to do the evaluation. So every solution here is checked against rigorous hidden test sets to ensure the correctness and also avoid the kind of rating inflation we've seen in the previous benchmarks. And beyond the pass rates, we calculate estimated error ratings. So results are directly comparable to human players. And because we run this ongoing contests together with the other players, so we can even check rating changes over time. And then for each problem and submission, our expert team will also conduct a fine-grained annotations and analysis, including topic tagging. We will assign each the topic, the first layer topic and secondary topic to every problem, and the problem will be categorized, and even each submission will be labeled about what is the root cause of the failure. And lastly, to better differentiate the model's capabilities, we ensure this benchmark covers a wide range of difficulties and problem types. And in addition, each problem is assigned an LO rating as its difficulty score. So it follows the tradition of code forces where so you will assume if the problem is the difficulty with some score, then the rating, like people with that rating have 50% probability to solve this problem. So this will provide us a very clear difficulty classification. So the difficulty tiers are very transparent and also consistent. Specifically, we have easy problem, which the rating is below 2000 and 2000, and the medium problems are between 2000 and 3000, and most challenging category includes only problems with a rating above 3000. So this may remain unsolved even by the strongest competitors during live contests. Then with this carefully crafted benchmark, addressing all the major issues we mentioned in the existing evaluations, we believe that we can finally measure the genuine performance of the most advanced models. So our main conclusion is very stunning, though perhaps not entirely surprising, that on problems that demand genuine creativity and reasoning, AI is still nowhere close to top human programmers. And at the time of writing this paper, all this model had a 0 pass rate on hard tire problem. And even the best model achieved only 53% on these medium tire problems with the LO rating of 2,116. So this means there's still a very significant gap between the AI models and human grandmaster levels, especially when these models operate without external tools. So we can avoid the search to answers directly. This is our main conclusion. And next, I'll hand over to Zerui, who will walk you through a deeper dive into the analysis and what we've learned from this data. Zerui, please go ahead.
Sure, yeah.
Peiyao, actually, this might be a good stopping point for a couple questions. I see one in the chat. Actually, we have a small group today, so Yue, do you want to just unmute and ask?
Sure, thanks, Rash. Just a quick question. Do you also evaluate on pass at n greater than 1? So do you also do like, multi-turn consensus ratings as well?
Yeah, so we have pass at 1 and pass at k, and k is up to 10. And Zerui will share the detailed results on this pass rate later.
Yeah. Awesome, thank you.
I'm curious, do you have a breakdown between the different failure modes that you kind of talked about for why, LLM performance is a little bit overestimated right now in competitive programming, like between the different categories that you broke down, like access to public solutions or any of the other categories? Like what do you think is the biggest kind of problem?
Yeah, so we have different classification of the problem itself. Like if it's a knowledge heavy one, it's a logic heavy, or it more relies on observation and those aha moment when solving the problem. So, and also for the submission, we will also classify different reasons of the failures. Whether it's implementation, definitely this is a strong point of those models, because if they know how to do it, then they will write a right code. But if they don't know the algorithm, or they cannot observe what is the key solving point of the problem, then they will be really bad at it. Even if you give it multiple chances, it cannot solve it.
Got it. Cool. Yeah, I think we can keep moving forward. We'll probably have more.
Sure. Yeah. Hello, everyone. I'm Zerui Cheng, a PhD student at Princeton University and a former intern at Shang. And now let me continue with the deep diagnostics. Headline numbers trigger deeper questions. Where do models excel and where do they break down? And let's dive deep into the diagnostics. First, we categorize all problems by cognitive demand. The first one is knowledge heavy, which usually require templates, deep understanding of algorithms and data structures, for example, segment trees and fast Fourier transform form. The second one is logic heavy, which usually demands step-by-step derivations, for example, dynamic programming and combinatorics. And the third one is observation heavy, which usually depend on aha insights that collapse the search space, for example, greedy algorithm and constructive tasks. And each category tests different cognitive abilities and represents distinct challenges for AI reasoning. Let's first take a look at the skill spectrum of LLMs. Plotting model rating across categories shows clear separations. Models excel on logic-heavy and logic-heavy tasks, but cluster lower on observation-heavy tasks. LLMs are strongest on segment trees, DP, and combinatorics, but they are weakest on greedy, game theory, and interactive tasks and casework. In short, they are precise and logical implementers, but lack in creative leaps. Furthermore, our expert team performed a line-by-line analysis of 125 failed O3 mini submissions versus humans with similar ratings, and the findings are: LLMs make 64% more conceptual errors than humans, misidentifying the right algorithm, yet make 63% fewer implementation mistakes once the logic is correct. Over 40% failed submissions fail on provided sample input-output pairs, which is 5 times that of humans, highlighting missing self-verification and a clear area for improvement. On top of that, we found out that multiple attempts matter. For O4 mini medium, the pass at 1 yields around 1793 elo, which is comparable to top 5% humans, while pass at 10 jumps to around 2334 elo, which is comparable to top 1% humans, which is a huge performance gain. Most performance gains are made on observation-heavy problems by multiple attempts, because guessing and testing different hypotheses without rigorously proving can help. However, hard-tail solve rate remain at 0%, showing the lack in foundational capabilities of solving really hard tasks. Also, it's worth noticing that even with pass at 10, there is a significant gap to the rating reported by OpenAI model card, and it highlights the power of external tools. Terminal access and web search explain the remaining 400 elo gap. Compilation checks, sample testing, brute force validation, and solution lookup all shortcut native reasoning, and again highlights the importance of liveness in evaluation. Without tools, native reasoning limitations become apparent, and with tools, models can iteratively debug and improve solutions. Finally, we compare DeepSeek R1 reasoning versus V3 non-reasoning, and Claude 3.7 solid reasoning versus non-reasoning, which reveals where explicit reasoning provides gains. We can notice huge gains in combinatorics and data structures, but minimal or even negative gains in observation-heavy categories. It shows that current reasoning methods excel at structured logic, but fall short on creative insights. Finally, let's briefly summarize the key implications from our findings. The first one, claims of surpassing elite humans, which is unfortunately not true today, need seriously qualification. Second, models excel at implementation precision, but not superior reasoning. Third, creative insights and observations remain uniquely human strengths. And fourth, claimed high performance largely driven by tool augmentation, not reasoning breakthroughs. Also, there is significant room for improvement in edge case handling and algorithmic creativity. And finally, from the perspective of evaluation, genuine live list is very important for future benchmarks to distinguish native reasoning from tool using. And in short, the gap to human grandmaster levels remains significant, especially in areas demanding novel insights and creativity. Then let's talk about open questions and start the discussion. Here is the roadmap for what is next for our project. The first one is problem creation. Can AI craft novel and hard algorithmic problems? And how would we ensure their rigor? And the second, model self-improvement. How might we enable models to test, critique, and refine their solutions without human in the loop? And finally, a recursive RL framework. What would an end-to-end loop of problem creation, evaluation, and targeted improvement look like in practice? And that is what we intend to do in our future works. And that concludes our talk today. And thank you for your attention.
Awesome. Thanks so much, guys. That was fantastic. We already got a lot of questions in the chat, so I think one is from Richard. Yeah, everyone can unmute, so yeah, feel free to just chime in. Richard, do you want to start? Kick it off.
Yeah, sure. Yeah. First of all, thank you for the great talk. So yeah, I just saw like a post recently on X, right? And then it shows that the GPT-5 High or the thinking mode is the only model that can successfully crack the hard problem. So
Yeah.
which is quite surprising because the rest are still 0%, right? So I wonder, have you like analyzed like their outputs, or what do you think might gives it the edge, or makes it like solve this problem better than the other models?
From my understanding, we have already tested GPT-5 High, and it has a nearly 10% solve rate on hard tier. And also, we are also testing Grok 4 now, because Grok 4 claims to have very similar performance as GPT-5. We just got the API credit from XAI team yesterday, so we will report the results soon. And from the output of GPT-5 High, from my perspective, it is much stronger in reasoning and identifying the correct algorithms. As we already found out that they are already very precise implementers, so once they get the correct logic, they can get the problems right. And now the major improvement of GPT-5 is on identifying the correct algorithms. And that is, in my opinion, a true reasoning breakthrough.